Right, so this is the final bit of this part of the course, with kind of the laws and the magnetic fields, because the next bits are more straightforward with the a bit about just analysing the kind of potential difference in the current that is produced from this, and then the operation of transformers. This bit, though, is the bit where we use Faraday's law, which is the EMF is the rate of change of flux linkage. So we did all these bits last video about finding how you calculate, how you find the value for n phi, which is flux linkage. And the rate of change of flux linkage is the EMF produced. And that's Faraday's law. And that's obviously important because that's the whole deal. We want to make electricity so we can do cool things. Now, that's Faraday's law. The next bit, Lenz's law. Lenz's law is a bit more confusing. Lenz's law tells us the direction of the EMF is produced, because EMF has a direction. It's moving electrons. They have a direction. And the EMF produced is in the direction that would oppose the change that caused it. Now, they give some tricky application questions of this. And I think this is a really tricky bit of the course. But the idea is if I move a magnet, a bar magnet, towards a coil, well, this coil, there's going to be, magnetic field lines here, right, all around the place here. And this coil is going to be cutting through the magnetic field lines. So the change being caused is this bar magnet moving towards this magnetic field. So the EMF produced to oppose the change is going to be creating a north pole here and a south pole here. So the magnetic field created in here by the current, by the induced EMF in here, opposes the change. And if you think about it, it has to do this, because if it didn't oppose the change, if I moved a bar magnet towards a coil of wire, right, if this was a bar magnet and I just moved it towards a coil of wire, and the wire created a magnetic field that didn't oppose that change, but instead welcomed it. So if it created a south-north, I'd move it a little bit and then it would get sucked in. So the magnetic field would, the attraction would take it the rest of the way, which would kind of violate the law of conservation. So if I push this in, the magnetic field created in this coil will oppose it, and so try and push it back out again. So pushing it in, and you get the opposite created. Now, so you kind of then have to reverse engineer what direction the current's going to be based on what magnetic field is created, or just not, the questions tend to be kind of superficial, I think, about with these magnetic fields, because it is tricky working out. Therefore, you have to use the right hand grip rule to work out what direction the field lines would be in, and it's a bit tricky, and a faff as well. And just they couldn't. Often it's just 50-50. Is it going to be north-south or south-north? It's always 50-50. So they don't want to give you more working for it, for something that can only ever really be 1 or 2 marks maximum, because it's a 50-50 guess. You don't know anything. You could just say, well, it's going to be north or south. So the force felt on the bar magnet will be opposing. Now, this only happens when it moves, right? As soon as this bar magnet stops moving, the magnetic field stops, right? So if I kind of push it through, it stops. So the magnetic field will disappear. The magnetic field only happens, do you remember, when we're cutting through flux? So when we're actually cutting through the field lines. So if I move the magnet away, right, the change is the magnetic field moving away. So to oppose it, it would create the opposite magnetic field, so that the bar magnet will be attracted. But then if the bar magnet stops moving, this magnetic field briefly disappears, will eventually disappear and then stop. And like I say, the questions are tricky. Right, so but that's Lenz's law. So whatever the EMF produced, the direction of the EMF opposes the change causes it. And often you get a negative on there, because this is the change, right? And this is the EMF, and it has to be in the opposite directions. But AQA just kind of don't just leave it out. So now, normally the application for this, and applications questions for this, can be related to a wire, a horizontal wire, a straight conductor moving in a magnetic field. So if I move this wire from there to there through this magnetic field that's going down into the page, I'm going to be cutting through all these field lines. So I'm going to be having flux linkage, well, just flux actually, because there's no coil. And the area that I've cut through and is going to be used to create the n phi, and then how much time it took is how I can calculate the EMF produced, right? So it might be that if it's moving uniformly at a constant speed, then it's easy to work out. Sometimes you get kind of tricky things. Now, What though we normally do is when we're trying to do this, or we make electricity, and to do that we have a coil of wire and we rotate it in a magnetic field like this. Yeah, so we don't rotate it like that, we rotate it in a magnetic field like this. Yeah, and rotating this coil of wire in this magnetic field is what generates electricity. The equation to generate this electricity is the EMF is equal to B, magnetic field strength, times the area, so the area that I've cut through. So for this one, for this coil of wire, the area, if I just do a half turn like that, I've cut through that area there of field lines. You have to figure out, but in this case, so it's just this area of the coil of wire, because that's the area that's being cut through. So you kind of sometimes have to use, they give these equations for the area of a circle on the front of the book, times n, the number of turns, times omega here. Now, this is from circular motion again, right? This is the angular velocity. So the angular velocity is 2 pi f, or 2 pi over t. So often they can tell you the frequency with which it's rotating, and then you have to use that to find the angular velocity, and then sine of the angular velocity times the time, right? Which essentially gives you the angle that it is at any given moment. Because again, same deal is at some points you're going to be generating no EMF when it's like this, so it's not going to cut through any coils as it kind of moves a little like that. But when it's moving from here to here, it's cutting through loads of field lines, right? Again, this is where I use my model. If it's here, not cutting through any field lines. If I had it in here, yeah, it'd be cutting through loads of field lines. But when it's like this, there's a little bit where it's not really cutting through anything. And when it's here, the EMF produced is 0. When it's here, perpendicular to the field, the EMF produced is maximum. So you get a kind of sine wave of EMF produced. And then the next topic is about, like, this is the electricity that we can produce. This is the trace of the potential difference for the EMF we produce when you plug anything in. And the next bit is a bit about, like, the math of that. But this is all in this topic. But I mean, it's hard, isn't it? Good luck.